Hi dear students, in the last presentation we have discussed about brittle fracture and we have seen the theory behind that fracture, that is what is Griffith's theory, which is applicable only for the brittle fracture. Now we will start this presentation with the topic stress concentration. The stress concentration is also known as stress risers. A stress concentration, also called a stress riser or a stress riser, is a location in an object where the stress is significantly greater than the surrounding region. So, as the name indicates, stress concentration means entire stress will be concentrated at a particular region of a material than the stress experienced by the other region. So, in a particular, if in an object at a particular region, if the stress experienced is more than that of the stress experienced in the other region of the material, then that particular area or region where the stress is maximum is known as stress concentration. Stress concentration occurs when there are irregularities in the geometry or material of a structural component that causes an interruption to the flow of the stresses. So whenever there will be irregularities in the geometry or material, see geometry means if the shapes are changing, like large bends, corners, etc. is coming. So these points, because of the geometry itself, they will usually act as the stress concentrators. And along with that, if the material, coming to the material side, if some micro cracks or flaws are there within the material, then that part is also going to be a stress concentrator. Usually the fractures are happening because of that type of stress concentration. So structural component that causes, so what happens is because of all this, the stress, the flow of the stress is interrupted. So the stress will be ultimately magnitude of stress at that particular point is going to be increased. അപ്പോൾ ഈ നമ്മളൊരു മൈക്രോ ക്രാക്സും അതുപോലെയൊക്കെ ഉണ്ടാകുമ്പോൾ നോർമലി ഉള്ള നമ്മളൊരു ഫ്ലോ സ്ട്രെസ്സിനുള്ളൊരു ഫ്ലോനെ അവിടെ ഇൻറ്ററപ്റ്റ് ചെയ്തിട്ട് ആ സ്ട്രെസ് അവിടെ കൂടി വരാനുള്ള പോസിബിലിറ്റി ഉണ്ട്. അങ്ങനെയുള്ള പോയിൻറ്റ്സിനാണ് സ്ട്രെസ് കോൺസെൻട്രേഷൻ എന്ന് പറയാം. So what happens is, if we apply a particular stress on a material, in practice what happens is the stress is not uniformly distributed all over the body. In theoretically we will assume that stress is uniformly distributed, but if some micro cracks are there within the material, then what happens is these cracks will going to act as a stress concentrators, or we can say the stress experienced at that defect points are very high compared to the stress acting on the other regions. Of course, that maximum stress will be much higher than the applied stress. So this will be contributing to the failure of the material. So while designing, all these factors are to be considered very carefully. Otherwise, the failure will take place. Okay. In case of fracture, very small microscopic flaws or crack. Flaw is also known as, flaws means actually it is microscopic levels of cracks is also, in simple word is flaws. In case of fracture, very small microscopic flaws or cracks are the principal stress concentration or stress risers. In case of the most of the fracture, I have already told, these flaws or cracks are acting as the principal stress concentrator and that are contributing to the failure. These are determinal to the fracture strength because the applied stress can be amplified or concentrated at the tip of these micro cracks. See, if a crack is there within the metal, I can show you the figure. See, this figure shows the elliptical crack within the material of size 2A. Of course, if we talk about the size of the crack, then we have to take it as a half the total size of the crack. We have to, if it is internal crack. So this is the elliptical crack of size A, I can say, even though its dimensions to A, crack size is actually expressed as A, and I am applying a normal stress of sigma A, of amplitude sigma A at both the ends, tensile stress I am applying. So at this crack tip, you can see this is the tip of the crack. At the crack tip, if you draw the stress strain diagram, it will be something like this. And here rho is the crack tip radius. Crack tip radius means, or we can say it is the radius of curvature of the elliptical crack. Okay, if you are assuming the shape of the crack as elliptical, then rho is the radius of curvature of this elliptical crack, or simply the radius at this crack tip. Okay, so the maximum stress will be at the end of this crack, either at this point or here. Okay, both the place we will have the maximum stress, and that maximum stress value is experimentally found to be sigma max equal to sigma A, where sigma A is the applied stress into 1 plus 2 into root A by rho, where A is the crack size and rho is the crack tip radius. See here, the sigma applied sigma is magnified by this much value, so sigma max is going to be very high compared than that of അപ്ലൈഡ് സ്ട്രെസ് സിഗ്മയ. നമ്മൾ കൊടുത്ത സ്ട്രെസ് സിഗ്മയാണ്, പക്ഷേ ക്രാക്സ് ഒക്കെ ഉണ്ടെങ്കിൽ എന്താ സംഭവിക്കുക, ക്രാക്കിൻ്റെ ടിപ്പിൽ എന്ത് സംഭവിക്കും, സ്ട്രെസ് കോൺസെൻട്രേഷൻ ഉണ്ടാകും. അപ്പോൾ അവിടെ ഉണ്ടാകാൻ പോകുന്ന സ്ട്രെസ് നമ്മൾ അപ്ലൈ ചെയ്ത സ്ട്രെസ്സിനെക്കാട്ടി ഒരുപാട് കൂടുതലായിരിക്കും. ദിസ് മച്ച് ഫാക്ടർ ഇറ്റ് ഈസ് ഇൻക്രീസ്. സി ഇറ്റ് ഈസ് ഡയറക്ട്ലി ഡിപ്പെൻഡിങ് ഓൺ ദി ക്രാക്ക് സൈസ്. ഇഫ് ദ ക്രാക്ക് സൈസ് ഈസ് മോർ മീൻസ് ദിസ് സിഗ്മ മാക്സ് ഈസ് ഗോയിങ് ടു ബി ഹൈ ആൻഡ് ഇറ്റ് ഈസ് ഇൻവേഴ്സ്ലി പ്രൊപ്പോർഷൻ ടു ദി ക്രാക്ക് ടിപ്പ് റേഡിയസ്. അപ്പോൾ എന്താ സംഭവിക്കുക, അത്ര ചെറിയ ക്രാക്കാണോ അത്രയും കൂടുതൽ സ്ട്രെസ് കോൺസെൻട്രേഷൻ നടക്കും. സി ഇറ്റ് ഈസ് ഇൻവേഴ്സ്ലി ഡിപ്പെൻഡൻറ്റ്. റോ ഈസ് ഇൻവേഴ്സ്ലി ഡിപ്പെൻഡൻറ്റ് ഓൺ ദി സിഗ്മ മാക്സ്. സോ ഇഫ് ദി റേഡിയസ് ഓഫ് കർവേച്ചർ ഓഫ് ദി ടിപ്പ് crack tip is less or very small means that much amplification will be there for the sigma max. So if you plot a graph, it will be something like this. See, at the crack tip sigma max will be the stress acting, and if you go along the distance from the crack tip, this is the distance from crack tip along the material, so distance from the crack tip, if we go away from the crack tip at a particular distance, then what happens is the stress acting will be equal to the applied stress. So there is a curvilinear variation, and after a particular distance the stress acting will be sigma A. See, even though we are applying a small force sigma A only, applied stress sigma A we are actually applying on the material, but since the presence of the crack, the stress concentration will take place, which will be much higher compared to the value of the applied stress sigma A. So in that case the failure can take place, and moreover this extra stress concentration will lead to the propagation of the crack, and finally fracture will take place. That is what is happening in case of ductile fracture. Okay, the stress amplification can also occur in the microscopic internal discontinuities like voids, sharp corners, notches, etc. അപ്പോൾ സ്ട്രെസ് ആംപ്ലിഫിക്കേഷൻ ക്രാക്കിൽ മാത്രമല്ല, അല്ലാണ്ട് തന്നെ വോയിഡ്സ്, ചിലപ്പോൾ മെറ്റീരിയലിൻ്റെ തന്നെ പ്രത്യേകതകളുണ്ട്, ഡിഫക്ട്സ് കൊണ്ട് വോയിഡ്സ് ഉണ്ടാവും, ഷാർപ്പ് കോർണേഴ്സ് ഉണ്ട്, നോച്ചസ് ഉണ്ടാവും. ഇങ്ങനെയുള്ളവർക്കൊക്കെയും കൂടി എന്തുണ്ടാവും, സ്ട്രെസ് കോൺസെൻട്രേഷൻ ഉണ്ടാവാറുണ്ട്. എഫക്റ്റ് ഓഫ് സ്ട്രെസ് റൈസേഴ്സ് ഈസ് മോർ സിഗ്നിഫിക്കൻറ്റ് ബ്രിട്ടിൽ മെറ്റീരിയൽ ദാൻ ദി ഡക്റ്റൈൽ മെറ്റീരിയൽ. That we will discuss in detail. Okay, while studying the ductile fracture we will discuss. In ductile material, large plastic deformation occurs when amplified stress exceeds yield point. Sorry, it is discussed here itself. In ductile material, I have already told that the effect of stress riser is more significant in the brittle material than in the ductile material. So what happens in the ductile material is, if the same thing is actually happening in the ductile material also. In ductile material, large plastic deformation occurs when the amplified stress exceeds the yield point. See, if a crack is there in a ductile material, so once we apply a particular stress on a material, say sigma A, applied stress is sigma A, if voids are there or microscopic cracks or flaws are there within a material, at the tip of that crack the ductile material also will be experiencing this same magnified stress or stress concentration. But because of that magnified stress, what happens is, if the developed magnified stress within the material exceeds the yield point, then what happens is plastic deformation will occur within the vicinity of that crack. Once the plastic deformation occurs, what happens is, we know that the strengthening of the material takes place in case of ductile materials because of the strain hardening that we have already discussed. So very near to that crack, actually the material becomes more strong, so the propagation of the crack is blocked there itself. So the fracture of the material in the case of ductile material happens because of the yielding only, or neck formation will be there, that we will discuss in later. This reduces the stress intensity near the vicinity of the stress stresses. So actually in case of ductile material also, if the cracks are there, because of the applied stress, stress concentration will be there in the vicinity at the tip of the crack at the tip of the crack or at the edge of the cracks. But that if the maximum stress exceeds that yield stress, what happens is deformation, plastic deformation will lead to the plastic deformation of the material in the vicinity of that crack. So once the plastic deformation happens, strain hardening will be there, the material becomes strong. So there won't be the much propagation of the crack only because of this stress concentration. So that is the difference between stress concentration in brittle material and the ductile material. In brittle material it is going to be very important. Okay. So this we have already discussed. Magnitude of amplification depends on the orientation and geometry of the cracks as given us in this figure. See the how much sigma max is produced is on the at the vicinity or at the tip of the crack. How much sigma max is developed depends on the geometry of the material as well as the orientation. See, it is depending on the crack size A as well as the crack tip radius or rho. Okay. Now coming to the next topic, effect of plastic deformation on crack propagation. How the crack propagation is affecting the plastic deformation, or simply this explains the ductile fracture. So ductile fracture occurs after considerable plastic deformation. It happens with slow tearing of the metal. So unlike brittle fracture, ductile fracture occurs after considerable plastic deformation. There was no plastic deformation happening in case of brittle fracture, whereas coming to the ductile fracture, before the fracture we can experience that plastic deformation or neck formation, I can say. It happens with slow tearing of the metal. Plastic deformation introduces strain hardening, which necessitates higher stress for the further deformation. See, once the plastic deformation is started, what happens is strain hardening is introduced within the material. So for to further deform plastically, we require to provide much more stress than the initial one. So which necessitates higher stress for further deformation. Plastic deformation reduces the stress intensity in the vicinity of the stress stresses, thereby avoiding brittle fracture. So this is the main reason why the cracks are there in both plastic deformation, in brittle fracture as well as the ductile fracture. But in case of ductile fracture, cracks will not propagate as such in the brittle fracture explained by the Griffiths theory. Here what happens is, because of the crack formation, if the since the plastic deformation is taking place in the ductile material, so once the cracks are there, but vicinity of the cracks will be getting hardened because of the strain hardening. So it will not propagate as such in the case of the brittle material. Ductile fracture is preceded by localized reduction in area called the necking. So how we can experience that ductile fracture is, initially if we apply stress, and if the stress exceeds the limit of the yield stress, then what happens is plastic deformation will take place. So ductile fracture is preceded by localized reduction in area called the necking. So initially we can experience a neck formation in the material before the plastic deformation, just at the time of plastic deformation is started. So that you can see from this here. So the neck formation is the starting point of the ductile fracture. So where, in which region neck is forming actually depends on in which region more stress is acting because of the applied stress. See, some voids or cracks will be there within, or we can say in the weakest region the neck is going to be formed. Okay, ഏറ്റവും വീക്ക് ആയിട്ടിരിക്കുന്ന റീജിയൻ ഏതാണോ അവിടെ ആയിരിക്കും നമ്മൾ നെക്ക് ഫോർമേഷൻ സ്റ്റാർട്ട് ചെയ്യുന്നത്. അല്ലാണ്ട് നമുക്ക് എപ്പോഴും ഒരു റോഡ് നമ്മൾ UTM മെഷീനിൽ വെച്ചിട്ട് ലോഡ് ചെയ്ത് കഴിഞ്ഞാൽ ഒരിക്കലും എന്താവില്ല, അതിൻ്റെ മിഡിൽ വെച്ചിട്ട് നെക്ക് ഫോം ചെയ്യണം നമുക്ക് പറയാൻ പറ്റില്ല. എവിടെയാണോ വീക്ക് റീജിയൻ ഉള്ളത്, അല്ലെങ്കിൽ ഇന്റേണൽ ക്രാക്സ് ഒക്കെ ഉണ്ടെങ്കിൽ ആ റീജിയൻ എന്തായിരിക്കും, ഇറ്റ് വിൽ ബി വീക്കർ ദാൻ ദി അതർ റീജിയൻ. സോ വെനെവർ there is a weak region within the material, neck formation will start within that weak region. Anyway, the starting point of the ductile fracture is the neck formation. So area called necking. It exhibits 3 stages after necking, namely cavities formation. So after neck formation, it has 3 stages to undergo. The first one is cavities formation. You can see it from the here this region is the cavity formation. So because of the applied stress, I have already told, in the weaker region only the neck formation will start. Initially there will be some small cracks, so small voids or cavities will be we can say, because of the applied stress, the crack or the void or the cavities formation within that neck region will increase. More and more cracks will form within that neck region. Then comes the cavities, coalescence and crack formation. So these cracks will interact together and there can be I have told that there won't be crack propagation as such in case of brittle material, but here cavities can coalescence, that means they can join together and crack can be become further bigger and bigger. So crack grows outwards in the direction perpendicular to the stress direction. So because of the applied stress, actually the crack is propagating initially perpendicular to the direction of this applied stress, as in the case of the brittle fracture. But I have already told, since plastic deformation is taking place in the case of ductile material, so always there will be shear stress acting along with the normal stress. So more or less, if the stress exceeds that yield stress, what happens is the dominant phenomenon that leading to the crack will be having crack will be the shear stress also. So shear stress also is having some importance. So because of the effect of both normal stress as well as shear stress, the cracking is taking place. So always after a particular limit, the crack propagation will be having some effect on the shear stress also. So instead of that 90-degree or perpendicular, the crack propagation perpendicular to the direction of the applied stress, that direction will change towards the 45-degree, since both shear stress as well as normal stress will be there as a reason for the cracking. So the ultimate effect will be at an inclined direction. So in one direction, along the force applied direction, normal stress will be acting. So in the perpendicular or the other direction, the shear stress will be acting. So the combination of these two, because of the combination of these two forces, stress will be developing at an angle 45-degree. So final fracture involving rapid propagation at about 45-degree to the tensile axis. So the propagation, see in the cavity formation, we have seen small cavities or cracks are formed because of the applied force and deformation within that material in the neck region. So these cavities combined together or coalescence will take place, and the larger crack is formed. Crack grows at 90-degree to the applied surface. So initially that because of that coalescence, the cracks will form as a bigger crack, and it will be moving initially in the perpendicular direction, as in the case of the brittle fracture. But once the plastic deformation becomes dominant, what happens is shear stress also will be acting. So because of the effect of that shear stress, the direction of the propagation of the crack will take a deviation to the 45-degree to the maximum shear stress value. So finally the fracture, since it is moving in a crack is moving in a 45-degree, it can see finally once the fracture happens, it will have a shape of cup and cone. See this cup and cone shape will have almost a angle of 45-degree like this. So this surface here, this angle will be around 45 degrees. Here also it is around 45 degrees. So always the ductile fracture is characterized by a cup and cone shape at the end of the fracture. And I have told, after rejoining it will not get the original shape. That is also an important thing. The reason is because of the extensive deformation at the neck region. So this is all about the ductile fracture. Now transgranular and intergranular fracture. See, we have now seen both ductile fracture as well as the brittle fracture. So in both cases the crack propagation is different. So that is what is explained here as transgranular and intergranular fracture. So transgranular fracture passing through the grains is called the transgranular or intragranular fracture. If the fracture is directly propagating through the grains, cracks change direction from grain to grain in transgranular fracture. Brittle materials usually fail in transgranular fracture. Usually this transgranular fracture happens in case of brittle material. You can see it from the figure. See, the crack propagates within that see in this sphere, the cracks are propagating within these grains. Okay, so that types of fracture is known as transgranular fracture. From grains, this is one grain, this entire bounded region is one grain, this one is another grain, like that grains are shown here. So the cracks are propagating within that grain, they are not passing through the boundaries of the grain. Instead they will be directly crossing through the grains, and from grains to grain direction changes also will be there. Okay, so such types of fracture is known as transgranular fracture or intragranular fracture. Within that grains the fracture will propagate. So these are happening in case of brittle material, whereas coming to the intergranular fracture, you can see the cracks always propagates through the grain boundaries only. You can see this is the grain boundary, here this is another grain boundary. So here 1 2 ഇവിടെ രണ്ട് ഗ്രെയിൻസ് ഉണ്ട്, കൺഫ്യൂഷൻ ആവേണ്ട, ഇതിൻ്റെ ഇടയിലൂടെ ഒരു ബൗണ്ടറി ഉണ്ട്. സോ here in this case of intergranular fracture, the crack is propagating only through the grain boundaries. It will not cross the grains, or it will not move within that grains. That is what that types of fracture is known as intergranular fracture, and mostly it will be taking place in the case of ductile fracture. Intergranular fracture, fracture along the grain boundary is termed as intergranular fracture. From that word itself, it is the intergranular grains in the adailuda. So in between, what is there? It is grain boundaries. So indirectly, it is if the crack propagates through the grain boundaries, then we will call it as intergranular fracture. Fracture along the grain boundaries is termed as intergranular fracture. It occurs when the grain boundaries are weak and brittle due to deposition of brittle phases. Okay. So that is the difference between transgranular and intergranular fracture. It is there in your syllabus. That's why discussed. Okay. Now another important thing mentioned in the syllabus is fracture toughness, and they have mentioned we need only the definition of fracture toughness, and so I am not going deep into this point. So fracture toughness measures the ability of the material containing a flaw, a microcrack, to withstand the applied load. So it is defined as the ability of a material uh, to withstand the applied load if it is having a micro crack within this. Why that word is added is, see, if a micro crack is introduced or is there within the material, of course stress concentration is going to be happening there. So because of that stress concentration, actually, even though we are applying only a very small stress on the material, at that stress concentration region, much higher magnitude stress is going to be introduced or acting. So the material will of course fail because of that high stress acting at the tip of that micro crack. So the ability of the material, if we calculate based on the applied stress, will be much less compared to the actual ability. So that fracture toughness is calculated with that high stress concentration. So fracture toughness measures the ability of a material containing a flaw to withstand applied load. So because of that stress concentration, the material will fail before the theoretically calculated maximum stress. നമ്മൾ തിയറി വെച്ചിട്ടിപ്പം ക്രാക്സ് ഒന്നും ഇല്ലയെന്ന് വിചാരിക്കുക, നമ്മളപ്പോൾ അതിനെന്തുണ്ടാവും, ഒരു ടഫ്നെസ് ഉണ്ടാവും. നോർമൽ ടഫ്നെസ് എന്താ, എബിലിറ്റി ടു വിസ്റ്റാൻഡ് ഫ്രാക്ചർ ആണ്. അപ്പോൾ അതിനൊരു ടഫ്നെസ് വാല്യൂ, എത്ര സ്ട്രെസ് വരെ അതിനുള്ള അപ്ലൈ ചെയ്യാം, അത് ഫ്രാക്ചർ ഉണ്ടാവില്ല, ദാറ്റ് ഈസ് ടഫ്നെസ്. അപ്പോൾ നമ്മളെന്ത് ചെയ്യുകയാണ്, ക്രാക്സ് ഉണ്ടാകുമ്പോഴെന്താ, നമ്മൾ അത്രയും സ്ട്രെസ് ഒന്നും കൊടുക്കേണ്ടി വരില്ല, അതിന് മുന്നേ എന്താ മെറ്റീരിയൽ ഫ്രാക്ചർ ആകും. അപ്പോൾ അതെന്തുകൊണ്ടാണ്, ആക്ച്വലി സ്ട്രെസ് കോൺസെൻട്രേഷനോട് അവിടെ ഹയർ സ്ട്രെസ് വരുന്നതുകൊണ്ടാണ്. ക്രാക്സ് ഇല്ലാത്തൊരു മെറ്റീരിയലിനെ സംബന്ധിച്ച് ഏത് സ്ട്രെസ് വരെ അത് വിസ്റ്റാൻഡ് ചെയ്യുമോ ആ സ്ട്രെസ് ഈ സ്ട്രെസ് കോൺസെൻട്രേഷൻ വഴി ക്രാക്സിൻ്റെ അടുക്ക് വന്നു കഴിഞ്ഞാൽ എന്തായി, മാക്സിമം സ്ട്രെസ് അതിനോട് ഈക്വൽ ആകുമ്പോൾ എന്ത് സംഭവിക്കും, അവിടെ ഫ്രാക്ചർ സംഭവിക്കും. സോ ഫ്രാക്ചർ toughness stress value will be always much lesser compared to the actual toughness value. The fracture toughness is measured by tensile loading of a specimen containing a flaw of known size and shape. So if we know the size and shape of the crack within the material, and the fracture toughness is measured by tensile loading of that particular specimen. Okay, the flaw acts as a stress riser and the intensifies the stress near it. A parameter called the stress intensity factor K is used to determine the fracture toughness of most of the material, and that intensity factor is mathematically given as K is equal to F into sigma root pi A, where F is the geometry factor because this stress intensity factor K is depending on the geometry of the material, if even it is depending on the thickness. So some geometry factor is introduced. It is a complicated equation, so a lot of things are to be considered, but we need only the definition of fracture toughness. I am not going in deep into that area. Stress intensity factor K is equal to F into sigma root pi A, where F is geometry factor for a specimen, sigma tensile stress or applied stress on that material, that is sigma, and A is the flaw size or the crack size. Okay, so Kc is the critical value of K above which the flow propagates and leads to the fracture of the material. So even if we apply stress, the flaws will or the crack will propagate only after a critical value of the stress applied. So Kc is the critical value of the K above which flow propagates and leads to fracture of the material. It is called fracture toughness. Kc depends on the specimen thickness. See, Kc is the critical value. So once the K value stress concentration intensity stress intensity factor reaches to the value of Kc, then the crack will start propagate. If the stress intensity factor K is less than the critical value, then the crack will not propagate. So Kc is the critical value of K above which the flow propagates and leads to the fracture of the material. It is called fracture toughness. Kc depends on the specimen thickness. When the specimen thickness is much greater than the flow size, Kc is constant. See, if the specimen thickness is much greater than the flow size, Kc is constant. It is then called K1C, plane strain fracture toughness. K1C is a material property. It has a unit of megapascal per megapascal root meter, or megapascal into meter raised to 1 by 2. So see, actually if you go through this topic, you can see three types of K is actually defined. One is Kc, that is critical value, and one is K1C, one is K2C and K3C. So these three types of K values, stress intensity factor values, are defined. So we will be talking about K1C only. When the specimen thickness is much greater than the flow size, Kc is constant. It is then called K1C, plane strain fracture toughness. It is called plane strain fracture toughness, and its unit is given by unit is given as megapascal root m. Okay, so those who are interested, K2C and K3C, you can refer this area. But here in our syllabus only we have to define fracture toughness. Definition only required, so I am not going in deep into that subject. Okay, thank you. Now in the next presentation we will be discussing an important topic, that is what is known as ductile to brittle transition. Okay, thank you.